Up until now, I've stayed entirely without mentioning a lattice. I've told you about liquids, and I've told you about electrons, and I've told you about classes of theory that can be written down without admitting that the electrons are moving in a background crystalline lattice. Of course, real electrons in real solids do move in a lattice, and nowadays we can take almost any solid and do a photoemission measurement on it, and we can measure as the Fermi surface, and the Fermi surface that we measure is going to be taking into account not just the lattice potential but also the electron-electron interactions. So we're highly used to thinking that that many-body Fermi surface that we've measured is going to be affected by the physics of correlation. And we're all used to the idea that we need to be thinking carefully about the electron-electron interaction energy U and its relationship with the electron kinetic energy W. Right? And typically when we think about the field, those are the only two energy scales we worry about. You often see U to T or U to W. It's Hubbard model language, but it's used widely. If you're trying to think about symmetry-lowered electronic structures in a lattice, you have to be very careful, and this is one of the reasons why I think they're quite rare, because you can't forget. So typically we forget the lattice potential and its role when we're thinking about many states. But of course, if the lattice potential is extremely strong and it's binding your electrons very strongly to the symmetries of the lattice, it becomes energetically unfavorable to undergo a transition like a Pomeranchuk distortion, where the conduction electrons try to adopt a lower symmetry than the symmetry of the host lattice. And the key problem that you face is that we're used to the idea that we know tricks of how we change the U to W ratio in solids, but it's actually very difficult to change the bandwidth, the kinetic energy, without changing the potential energy, the lattice energy. So in general, as you try and make a solid more interesting by making the correlation strength closer to the bandwidth, you're also cranking up the lattice potential, so whatever state you get has a higher probability of respecting the symmetries of the lattice. So what you need to do for the electronic liquid crystal game is to find a way of breaking this. You want to be able to tune the bandwidth independently of tuning the lattice potential. And I'll try and cast the experiments I tell you about in those terms. The other thing which really complicates interpretation is that the highest symmetry, in the liquid crystal case, the highest symmetry you begin with are the full symmetries of the isotropic liquid. The highest symmetry you start with in a solid is the symmetry of the lattice, which is determined by this lattice potential. However, the electrons then make a Pomeranchuk distortion, say. They still have some finite coupling to the lattice, so if the outer electrons adopt a lower symmetry state, the lattice will respond to that. So you can get, and so you can't, in the solid, define these liquid crystalline states purely or easily in terms of symmetry, and I think there's a lot of confusion about that. You end up with this kind of chicken and egg problem, where what you're trying to decide is, did this lowering of symmetry have its origin in the electron-electron interactions, or did it have its origin in structural chemistry? Right, but that's a decision you have to take, and there's a lot of completely wrong and very loose language in the literature about this. You always have to be aware there's going to be a back coupling. Okay, so real experiments. The first experiment from the late 1990s, almost exactly 40 years after Pomeranchuk, the first one that convinced people, I think, was done by Jim Eisenstein's group. And he was studying extremely high purity two-dimensional electron gases. And he was asking the following question. He said, if we have an electron gas which is such a high purity that when I go to ultra-high fields I see the fractional quantum Hall effect, I know that if I go down to much lower fields I retain a Fermi liquid. Does anything happen in between? And so he started to look at not the lowest Landau level where the fractional quantum Hall effect took place, but he started to look carefully at the properties of Landau levels between there and where he had the Fermi liquid. And what he discovered in those Landau levels, there's two Landau levels below the fractional quantum Hall state, in which he discovered that a system which seemed to be isotropic in the x and y directions in all the other Landau levels went very anisotropic for these 2 Landau levels. And that carried a lot of credibility because somehow he was doing a tuning from a definitely isotropic to a definitely anisotropic state, and it was extremely difficult to see in a device how that could possibly be coming from any structural effect. That had to be an effect of the electron-electron interactions in some way.
Sorry, there is a magnetic field there, right?
There's always a magnetic field, so this is in a perpendicular magnetic field. So the magnetic field is perpendicular to the layers, but the anisotropy is lying in the layer, right? And the anisotropy seems to be tuned by some detail of the device, because actually X and Y, one should be favored, but they should always be degenerate. So you always need something to help you choose X over Y. And in these, some details of the device do it. But even in that 2010 review article, Eisenstein's section of that said that they don't fully understand in the devices what's selecting X over Y yet. So you might ask yourself, why is this happening? And here I think it's where you get to these energy scales. This is a very low density semiconductor, so U is very small. The interaction term compared to a correlated material is very small. So is V, because you're down at some very long wavelength where you're not feeling the lattice at all. So you would think that W would dominate and you'd get nothing interesting going on at all. But of course the essence of all the interesting physics that happens in high magnetic fields is that when you split into Landau levels, you kill the bandwidth. So you kill the kinetic energy by putting things into Landau levels. If you kill it well enough, you get the fractional quantum Hall state. But these 2 Landau levels appear to have just achieved the balance to be just right, so that the leading instability is a Pomeranchuk distortion of some kind. It's an instability towards anisotropic transport. So these were highly influential experiments, and I guess it was very gratifying indeed to Kivelson and Emery and Fradkin that it happened only a couple of years after they first wrote the paper saying that one should look for these things. And this is the other point experimentally. If you assume that your solid always respects the lattice symmetries, then you never bother explicitly looking for anisotropy, and you certainly don't find anisotropy if you don't look for it. So another of the influences that these theory papers had was to cause experimentalists to check whether they had an isotropic system or not. Okay, so now we begin with high temperature superconductivity, and let's review a little bit about what happens there. And here the source paper to my taste came from Yoichi Ando's group back in 2002, although there were famous observations of stripe-like ordering in lanthanum, strontium, copper oxide before that, if you're an expert. But this paper wasn't widely accepted when it first came out, because it seemed to be making a rather roundabout argument. So this high-temperature superconductor has planes of copper and oxygen, but it also has copper-oxygen chains. So it's actually quite a strongly orthorhombic structure. It's twofold symmetric already, right? And therefore, people had done a lot of work looking up here at where they found that red here means there's a strong transport anisotropy. That wasn't a surprise to anybody, because everybody expected that in a very anisotropic structure you would see an anisotropic response. But what Ando pointed out was that they could carefully make these superconductors with different oxygen content, and as they made the oxygen content smaller, the level of orthorhombicity went down, but they reached a level at low doping where the thing was almost tetragonal structurally, but the anisotropy came back. So their argument was that you would find static stripes. It turns out 10 or 15 years later that you don't find static stripes, but this anisotropy is now relatively widely accepted to be a feature of the conduction electrons and coming from interactions within the conduction electron gas. And it's likely to be one of these melted stripe type nematics, because this is quite a strong coupled system. The whole thing was given a lot of impetus by a neutron scattering experiment done by Bernhard Keimer's group, where they began down at the doping where Ando had seen the transport anisotropy. And if they went up to a high energy and did an inelastic neutron scattering measurement and tried to look at the line shape in X and Y and Kx and Ky space, they saw something pretty much isotropic. That wasn't a surprise. But when they went down to lower energies, they discovered that isotropic line shape systematically distorted to become strongly elliptical. So they reported that this meant that the spin response of this ITC superconductor mimicked the charge response, and it seemed to be evidence for microscopic lowering of the symmetry within this state. And then there's been some work on thermoelectric coefficients led by Tai Fer's group in Canada, which also confirmed that this anisotropy sets in. So I think in the high TC materials, certainly in yttrium barium copper oxide, it's now widely accepted that there is some form of an electronic nematic state in the phase diagram near the superconductivity. And we'll come on later to the relationship that that might have with the superconductivity. I think the plot thickened even further and things became even more interesting when the pictides were discovered and people began to look at the pictide phase diagram in more detail. This, I think, has been led by Ian Fisher's group at Stanford. And here you have rather similar kind of phase diagram to the cuprates in many ways. You have superconductivity with a tantalizingly high critical temperature. Then you have a structural transition. Then you have an antiferromagnetic transition, so you have structural order, then you have spin order. But when you study the map of the anisotropy and you compare it to the anisotropies associated with these transitions, you see that it's peaked in the wrong part of the phase diagram. So in this case, the material should be getting more crystallographically orthorhombic as you go down to low temperatures and low dopings, but the anisotropy is getting more isotropic electronically. So that caused Fisher's group to postulate that you had something going on from the electronic system that was driving the strong anisotropy that you were seeing here. But of course, this is all a bit messy. You know, you can get into many arguments at conferences making statements like that in the presence of structures which aren't really tetragonal. So I think then, though, that Ian did a very smart experiment which increased the credibility of the whole thing a lot. So what they thought was that, okay, all the time here, they couldn't even observe this anisotropy unless they had pre-stressed the crystals, because the crystals have crystallographic twinning going on, and if they were strongly twinned, then you don't see the macroscopic anisotropy because you have domains of the anisotropy going in two directions. So, like in every other case we'll come on to, there's some sort of a symmetry breaking, macroscopic symmetry breaking field required in order to see the gross anisotropy. So here it was this stressing to suppress the twinning. So then the Fisher group said, okay, we're going to try and glue our samples to piezo-resistive stacks, and we're going to try and explicitly do the experiment under conditions of constant strain. So we're going to try and keep the lattice constant of this sample constant as we lower the temperature, and we're going to see what the resistive response is as we do that. And the idea there is very simple. If it's structurally driven and you've suppressed the ability of the structure to change as you change the temperature, then you shouldn't see any change of the anisotropy or the tendency to anisotropy as you change the temperature. If, on the other hand, the anisotropy is fundamentally coming from the electronic system, it shouldn't care. And they did this rather nice experiment published in 2012, where they showed a diverging, now this is the resistive anisotropy's derivative as a function of the strain. So they hold the strain constant grossly, and then they wiggle it a little bit, and they see how the resistive anisotropy reacts. And they saw a beautiful lambda-like divergence of the anisotropy heading towards a well-establishable TC, which also actually wasn't exactly the same as the structural TC. Right? And so they were able to prove a lot of things here. And I think once people saw this experiment, they realized that there had to be excellent evidence that there was some form of fundamentally electronically driven anisotropy going on in this crystal. And certainly up at these temperatures, there's no signs of translational symmetry breaking at all. So you imagine this must be some form of electronic nematicity.
Sorry, Anne.
Yes?
This also means that the crystals are very sensitive to strain.
So there's
pressure or whatever it will.
Yeah, indeed. The pictides are extremely sensitive to strain. all of these arguments are based on symmetry, and symmetry doesn't tell you the coefficients. So there are some of the systems which are, there's some unknown parameter that tells you the strain sensitivity. Some of them are strongly sensitive, some of them aren't. And so obviously if they're strongly sensitive to strain, then there must be something pseudo-structural going on here, even though it's not driven by the positions of the nuclei. And what they believe, they've got very good evidence from photoemission that what's happening in the pnictides is a form of ordering of the orbitals. So it's the outer orbitals forming the chemical bonds which are ordering and giving you the anisotropy, which is why you would motivate that that probably does couple very strongly to strain. So now onto the material that we've studied a lot. And this is another metal. It's not a high-temperature superconductor, but it's an interesting so-called quantum critical system, strontium-3, ruthenium-207. And it consists of bilayers of ruthenium oxide separated by spacer layers. So there's a strong bilayer coupling of the electrons, but there's a very weak coupling between bilayers. So it should be thought of a two-dimensional stack of bilayers is essentially the way to picture what's going on. Almost all the charge flow is in the plane. And we've done a lot of work on this over the past 10 or 12 years. And what we're able to show is that in some senses it's a canonical quantum critical system. So here there are many things on this diagram. So first of all, look at the color from blue to red. This color coding is a cartoon trying to tell you that when it's blue, the resistivity is going as T squared, so it's the resistivity of a Fermi liquid. When it's red, the resistivity is going linearly in temperature, and this is often seen when you're tuning towards a quantum critical point. When you're sitting above the quantum critical point, for reasons that aren't very well understood, the resistivity is linear in temperature. This is one of the reasons people are interested in quantum criticality in the high TCs.
Sorry,
yes?
so in the left part, is there some order or something?
So that's, no, the other point is that this is what's called a metamagnetic system. It's a very interesting system. So what happens at this transition point, the main thing that happens is that the magnetic moment of the system jumps. So here it's, if you like, the low polarization state. This is the high polarization state, but it's exactly like the liquid gas transition. So you just have a thing of degrees. So